I think we can go ahead and get started. Thanks again for joining us. My name is Sally Ann. I'm a machine learning solutions engineer at Arize. With me today, I have Philip Gonzalez, and he's a software engineer. Super excited for our content. We're going to be focusing on building and troubleshooting an advanced LLM query engine. So it's going to be covering search and retrieval, or RAG, if you heard it by those other names. And before we get into the content, just want to go over a little bit of an agenda. So Philip, if we go to the next slide. So we're going to do an intro to LLM orchestration. We'll then move on to intro to vector DBs with a special focus on Milvus, of course. And then we'll do an overview of search and retrieval and cover what can go wrong before we dive into our interactive session for our Phoenix and Milvus workshop. We love this to be interactive, so as we go through the material, feel free to drop questions in either the chat or the Q&A, and we'll answer them as we go along or at the end of our session. So with that, I'll kick it off to you, Philip, and take us away.
Awesome. Yeah. So hi, everyone. Thanks for joining us. I guess you already kind of heard the overview of what's going to be going on. So I'll just jump right into it. So the first part we're going to talk about is LLM orchestration. In this kind of demo / example that we're going to be bringing out, we use two of the most popular libraries, LlamaIndex and LangChain. There are a few more coming out, but I think pretty much everyone knows these two projects. So I'll quickly go over what they are and then sort of how they're different. Let's start with LangChain. So LangChain advertises itself as an LLM application development framework. And what this means is that it's a project built of agents that let LLMs kind of act in different ways. So if you want to kind of apply an LLM to write an email, you can create an email agent that can start writing these emails for you. And let's say you want to pull data, post data somewhere, kind of anything that you could do programmatically, you can create an agent that can connect to an LLM and kind of act in that programmatic way. And that's mainly what LangChain is. LlamaIndex is a little bit different there. LlamaIndex is a data framework for LLM applications. And what that means is LlamaIndex is in charge of kind of bringing in data from everywhere. So let's say you want to bring in all your PDFs from a directory, all your chats from a Discord, data from a vector database, data from a regular database. You need some centralized way of connecting to all these systems and kind of having one centralized way of understanding that data. And a lot of these projects kind of have this format of a document as the main data storage type, where metadata and different text data can be stored and kind of accessed. And this is where LlamaIndex comes into play. It's really good at kind of parsing all these different types of data and bringing them in like a singular format that then LangChain can kind of connect to and then act on that data. So LlamaIndex is kind of the step before LangChain normally. LlamaIndex is great for if you're just trying to pull data, or maybe you want to create like a simple little chatbot. That's where it kind of excels. LangChain more for situations where you have either a lot of agents running, multiple LLMs acting with each other and speaking to each other, or just multi-step kind of pipelines. And both projects are slowly kind of growing into each other, which is kind of funny. Each one's kind of expanding into each other's domains. So we'll see kind of how this continues forward. But for now, that's kind of how they're different. I know that question pops up quite a bit when looking at these two projects. So hopefully that sort of makes a little bit of sense and kind of gives more details into why you'd want to pick one and not the other, or why you'd want to use both of them. The next step is kind of bringing in this idea of memory to LLMs. And this is where vector databases come into play. As I said before, LlamaIndex can kind of connect to these vector databases and use them as kind of a memory store and a place to put data and pull it out later for when you're kind of wanting to speak on a specific subject or something like that. And what vector databases are perfect for is kind of bringing back useful data for an LLM to summarize. So this kind of lets you bring in your own data. Let's say you have a bunch of data about how to build a car, where there's a bunch of documents for each step and yada, yada, yada. And you want to ask an LLM, like, what comes after putting the engine in? Well, sometimes if you use just a regular LLM, let's say it doesn't have this in the training data, it probably does, like OpenAI and these guys, they probably trained on all this kind of data. But let's say it doesn't have it, it might give you a response saying, oh, I don't know, I wasn't trained in time. Or another response that it might give is just might make something up. So if we kind of give this ability to bring in relevant documents, I can search for a document that has maybe that's semantically similar to engine or steps after engine, and take that document in and have the LLM summarize on it. And this is pretty useful because it kind of brings a sense of proof to your answers. It's not anymore either something completely made up or no answer at all. There still is some area for hallucinations to occur, and hallucinations are kind of this making up of data, because the LLM can still make up some data while summarizing a document. So it's not completely foolproof, but it does kind of allow you to trace down where some answers are coming from and how good those answers are, and if you kind of need to update some of your corpus knowledge. So let's go over vector databases. So what they deal with is unstructured data. So in the previous thing that I mentioned, maybe it's text documents, maybe you want semantics from text documents. It could be audio, it could be videos, images, pretty much anything that can be stored. And the reason you need a vector database is because computers don't really have a good way of understanding this type of data. So like, let's say you have an image, if you rotate the image by maybe a few degrees, all the pixels won't line up anymore. And if you're trying to compare to images, use some kind of rudimentary way of doing it, the images will be completely different. There won't be any similarities because every pixel will be off by some amount. Recently, though, I guess semi-recently, it's been quite a bit now, we got deep learning models. And what deep learning models kind of allow us to do is give the computer kind of a way to understand that data. It can kind of break that data down into pieces of data that it understands. And then it can also compare this data. So in this case, we're using these models to create embeddings, and embeddings kind of put all your data in a latent space where things are comparable through distance. And this latent space is made up of these vectors. And that's what we store. So we store those vectors that kind of show the meaning behind your data and allow you to kind of search for similarly marked data. And this is kind of becoming really useful because I think there's a statistic lately that said that 80% of all data at this point is unstructured. So we need a way to handle all that data and a way to kind of make inferences based on that data and kind of extract knowledge from this data. So how do we do this? Normally, like, you could technically use a relational database, store each vector as, let's say, a row, and then brute force search across this data, but this is really slow. Way too slow for any kind of use cases. If you're searching over millions or billions of vectors, doing a brute force search every time you want to find the closest 10 matches is not going to be a solution. And this is where these indexing algorithms kind of come into play. And the reason that they're very important is because they allow us to index these distances and kind of create these structures that allow for much, much faster searches. Here I just kind of displayed 3 different types. We got the inverted file, the tree-based, and HNSW, which is a graph-based. The inverted file, if you've kind of been in this area, most of these will be the IVFs from Face, which is a open source project that kind of kickstarted a lot of this indexing work. And I think Facebook's using that internally under the systems for a lot of their searching. And what this is pretty much k-means clustering. As you can see in the image below the inverted file, those are the Voronoi diagrams that kind of show clusters. And the way that this works is you do k-means clustering, and then if you have a vector, you find the closest centroid and then search the remaining vectors within that kind of cluster. And this is a pretty basic one. This was one of the first. We have Voronoi, which is Spotify's open source project, open source index project. And I'm not sure if they're still using this. Unfortunately, we kind of removed this one. It wasn't getting a lot of use case, but it's a cool one to look at because it's based on random tree splits. And the way this works is that you take your data, kind of this multidimensional data, and you start splitting based on a hyperplane. And you try to aim for like equal splits. I don't think Voronoi does it currently in its current form, but you keep splitting your data and then you kind of make this tree. And then with a forest of trees, you can go down by searching, and then you just decide, is the left side or the right side closer? And you keep going down and down until you kind of get your points of interest that could be the top K results. Last one is HNSW. This one's a graph-based index, and it's based on a skip list and the small worlds navigable graphs. I think that's NSGs. But this one, pretty much you start with a very sparse graph, and then you kind of find your long connections on top. And then each layer you go down to kind of find the closer and closer connections to the sparse ones from the top. And yeah, this is HNSW, another open source project. And probably one of the most used. I believe most vector databases these days are using them. It's the fastest. Normally has the most memory requirements, but it is the fastest, and everyone's using that. So why do you need a purpose-built vector database? Using these libraries doesn't really offer a lot in terms of backups, in terms of filtering, durability, replication. None of this is really offered. These libraries are just kind of a way to make an in-memory example and kind of use it. So we need a vector database to kind of offer all these things. We need filtering. So we need to filter, let's say, on either distances, like a range search. We need to filter on metadata that's attached to the vector, let's say the text, or maybe when it was created, the time it was created, something like that. We need durability. So everything's durable. If things go down, things can come back up. You won't lose your data if your memory crashes, which in terms of base HNSW in these libraries, there is a way to kind of back them up to slow storage, but it's not really efficient and it doesn't do it automatically. So you need durability, replication, high availability as kind of come into play with durability, guarding for kind of increased throughput, faceted searches. So that's also kind of this filtered search, backups, lifecycle management, multi-tenancy, all these things that you will kind of need when you're building up these systems. And then why Milvus? So like a little spiel that I want to bring in for Milvus is because we are kind of a separated compute and storage. So this allows kind of separating out and scaling each kind of point of each use case of the data. So let's say you're doing a lot of insertions, you can scale up your indexing and your data insertion nodes. And if you're not inserting a lot and you're just querying a lot, you can increase how many query nodes and decrease the rest of the nodes. And this kind of helps you save money, and it kind of makes the system easier to run, and you don't have to worry about not using all your resources. It offers full precision recall. It offers all those indexing libraries that I mentioned before. Also offers GPU support. NVIDIA GPUs, they came to us and helped us kind of build up their indexing libraries. And we also support up to the billion plus scale. So that's pretty useful. And we have our own vector search library that kind of incorporates all those indexes that I previously mentioned, and we modify and improve them. And it's all open source. NVIDIA put some work into there. And yeah, that's kind of my spiel on why I think Milvus is the best choice. Now I will go quickly, or I'll let you take over. We can kind of go over the demo together at the end.
Okay, perfect. I did see there's a question in the chat that I think might be worth pausing and answering. So we have a question about, are the vector databases JSON objects of text chunks and corresponding vectors? Could you just clarify that for them?
Yeah, so pretty much, at least with Milvus, you can store any JSON data as pretty much another column in your row, if you kind of want to think of it that way. So you have a column for your vector, and you can have JSON objects, or you can have just a JSON of a bunch of different metadata. And then we support filtering across all that data, returning that data, storing that data. So yeah, you can pretty much attach any JSON data to a vector.
Awesome. Thanks for clarifying that. Cool. All right. Do you want to keep sharing slides, or you want me to take over?
You can take over.
Okay, perfect.
How do the vector databases store vectors? So in our case, I can maybe answer that at the end as well, if you want to just start your slides. I'll come back to that question.
Ahead. Oh, okay.
Oh, okay.
That works too. Oh, no, go ahead, answer. I think it's good. We have time. I love answering questions live.
So how do they store the vectors? Well, it's kind of in two formats. So at least with us, we store kind of the raw vectors that we store in slow storage, like offload to S3 just for data backup. But in terms of storing vectors and indexes, most of the indexes allow for the original vector to be there. So you're building these indexes. It's a separate file that kind of help you search based on like a primary key. Some indexes perform quantization, which kind of destroys your original data, compresses it down irreversibly. And those ones, you don't store the original data in the index. But the main way is you kind of build the indexes up and you use those for search. And if you need to grab your data back, you can sometimes directly pull it from the index, or you can pull it from your slow storage. Not sure if that kind of answered. There's a lot of different areas within this and how different things are. Okay, yeah. So yeah, but then how do you map text with vectors? That's just in memory. It's just a map. It's C++. But yeah.
Awesome. Looks like they got all the answers they were looking for. I think it's important to kind of discuss this because as we're going to dive into, all of this kind of relates into how these search and retrieval applications work. So I'm glad that we were able to have Philip give us a great overview of LLM orchestration and these vector databases so that we can now discuss search and retrieval use cases. So we're really going to zoom in on this use case now. Before we go over how it works, I do always like to talk about like why you should care about this, why we need them. Philip, you talked about this briefly in your section, but kind of reiterating that point here. So I think there's no better way to illustrate that than taking a look at an example from ChatGPT. So here we have ChatGPT. We've asked it, tell me about Arize, and immediately it says that it has no information as of its cutoff of September 2021. Arize is pretty new, so it didn't have any information on Arize in its training data set. Therefore, it doesn't really know how to answer our question, doesn't have any relevant context. What we can do is we can take our first page of our docs or like intro docs and give that to ChatGPT and then ask our question, tell me about Arize. And you can see here that it's able to give a much better answer. It's actually able to say Arize is a real-time machine learning observability and explainability platform. And so this is kind of simulating what search and retrieval does, right? So it's going to take a piece of context and pass that to the LLM before it gives a response. So it's really equipped with the information it needs to appropriately answer. And so kind of summarizing that, with search and retrieval, you're able to provide your own context and data. The second point, Philip, you touched on this earlier, is that we have grounded responses and trusted sources of information. So when you're using search and retrieval and you're storing your documents in your vector database, you're really able to have these trusted sources and not solely rely on the information that these foundation models were trained with. So that definitely has a plus to it. And then the last one is going to be that you're easily able to update output by swapping out documents from your knowledge base and index. So here you can really keep your LLM up to date with information. You're able to add context that's missing or maybe remove context that's not necessarily needed. And just overall, my big takeaway of why we need search and retrieval and why we should care about search and retrieval is it really empowers you to use your own information to power your LLM. So you're taking your proprietary data to your LLM and being able to build applications on top of that. So that's a little bit about why you should care about it. Let's discuss at a high level how it works. And so this is the overall process. The first one, this was talked about in Philip's portion here, is creating our knowledge base. So we're going to take our documents that we're interested or data that we're interested in powering our LLM with, and we're going to chunk it and embed it and store it in our vector database. So at inference time, we have a user query. They'll ask a question like here, how much does Arize cost? We'll then embed that query and send it to the vector database to find the most similar pieces of context. And so here we're using cosine similarity. There are other similarity metrics that you can choose, but this is the one we're choosing here. And we can see we're finding the most similar. So the higher the similarity, it goes from 0 to 1. The closer to 1, the more similar the document is. And here we're just grabbing one chunk. And what we'll do is then take that chunk and pass it with our user query as our prompt to the LLM to generate a response. So this is this process at a very high level. Let's talk a little bit about what problems can emerge. And so the way that these applications are typically deployed is we have a user query and then some question answering service. And challenges can arise even before you add in the search and retrieval component. And I think that's something important to remember because that just adds more complexity and therefore there are more problems. But let's discuss the problems before we even add search and retrieval. So the first one's going to be model hallucinations. Phil definitely talked about this one before. Again, that's when your model is presenting response as factual when it's indeed wrong. And this can be really tricky because it obviously can still happen in search and retrieval, but often happens, when you don't have the necessary information to answer the question. The second one is evaluation is hard. And this is kind of a multifaceted problem because there's a few different ways it can be difficult, right? The first one is when you have user feedback, it's hard to interpret what that user feedback means. Did they give you a thumbs down on the response because it was the wrong answer? Or did they give you a thumbs down because they maybe didn't like how the information was presented or they didn't like the answer they received? So interpreting that user feedback is hard. The second part of that is the fact that user feedback is sparse. I always like to call it the fact that whenever I use ChatGPT, I don't think I've ever given a piece of user feedback. So you can imagine that on a large scale. It's hard to get the users to give you that feedback and thus makes it difficult to identify those bad responses. So this is like before we even introduce search and retrieval, but when you do that, you're obviously having this entire process injected in this flow. So we're getting our user query embedding, we're sending that to the vector store, we're then enriching our prompt with that context from our vector store and then sending it to the LLM. And so this has its own set of challenges that can come up in your deployment. And so the first one is bad retrieval. So I mentioned that we're going to retrieve context from our knowledge base based off a similarity metric, but as we'll talk about, similar is not always relevant and that can cause a lot of problems. And just being able to identify where that bad retrieval is happening can be difficult. The second one is that there's no real visibility into the agent's performance. Again, just making it really hard to understand why your LLM is responding in the way it is. The good news is that Arize can offer you this foundation layer of observability. So we can ingest data from various parts of this pipeline and really provide you with the workflows and tools to troubleshoot these problems when they come up. And for today's session, we're really going to be focusing on this portion here, the bad retrieval and the search and retrieval system as a whole. So just want to kind of cover this all together now that we've gone over some potential problems before we really dive in. So these are the same 4 steps that we've been talking about: our user queries, searching for our documents in our vector store, getting that retrieved context, and then using that to generate our response. And so I already highlighted that, we can get bad responses, but when your LLM is giving you a bad response, it's not doing it for no reason. There's some underlying reason behind it. And so we might have an issue where we don't have any documents that are close enough to our user query, so we're not retrieving anything, and therefore the LLM is not able to respond well enough. The second one is going to be where the most similar is not the most relevant. So perhaps we have retrieved some context, but they're actually not the most relevant pieces of information. And so identifying these can be difficult, but that's why it's really helpful to have a tool like Phoenix or Arize to help you really not only identify when you have bad responses, but then actually go through workflows to root cause and therefore, or then to resolve your LLM's issues. So with that, we'll get to the fun part, our workshop here. So this is going to be focusing on Zillus from Milvus and Phoenix, our open source observability tool. And we have the notebook here. It was also just pushed into resources as well. So you can open the notebook and follow along if you'd like. If you have any questions, we do have a channel, Phoenix support. You can join from this link as well. It should be added to resources. And feel free to ask us questions as we go along. Let's jump to it. Philip, do you want to take over screen share, or do you want to just have me share?
I can take over.
All right, cool.
Let me know if it's visible. I think it's visible, right?
Yep.
Okay. Yeah, so this is just the notebook. I'll go over kind of the first half real quick. In the top, kind of it talks about what we've kind of gone over today and what you'll achieve. So if you want to take a look at that later, that's awesome. Here's the architecture. This is a pretty standard architecture, just grabbing embeddings, grabbing your data, embedding it, putting it within the Milvus instance, and then when you're going to search it, grabbing the embedding of the search question, searching for it within Milvus, and then pushing it back to the LLM to kind of synthesize a response with it. I'll just go over. So yeah, first we have some packages that you need to install. In terms of the PyMilvus package, PyMilvus does kind of conflict with the gRPC package of the collab. So it will prompt you to restart the runtime after running. We're working on kind of getting the latest gRPC, but for now, you'll kind of get this restart runtime button here. So after running that, restart it, and you can kind of start running from the top here. This is just kind of importing all our statements. We're using OpenAI for this, so I already ran this just to make sure everything works. So I'm going to leave it like that for now. But what you can do is when it prompts you for your OpenAI key, you can just kind of type it. I'd probably throw an error here, maybe not. Yeah, you can type it in, and that kind of makes it easy. So we're going to start by downloading the data. Luckily, Arize kind of hosts this data, and I think it's pretty much most of what's on their site is used as the data. So we're kind of answering questions about Arize. So yeah, we just grab the data as a JSON, and it has rows of text data. And this is kind of where we start getting into the Zillus Cloud / Milvus bit. Both of these work either open source Milvus or Zillus Cloud. Milvus, being a pretty distributed system, doesn't like it too much when it's run in Colab. We do have an embedded version, but just to be safe, we kind of went with the Zillus offering because all it requires is just a string and a password. So we just did it like that, but this can run with a Milvus instance if you want to use that instead. So the endpoint will just be, if you're using Milvus, it might just be http:/localhost :19,530. In this case, we're using our Zillus endpoint, And then for the token, if you're using from Zillas, you'll get a token. If not, you can just do an empty string for this if you're using Milvus. And what we're going to be doing is we're just going to be using the integration that we did with LlamaIndex to kind of create everything and set everything up. All you have to do is pass in the URI and token, give the collection a name. So the collection is kind of where you're storing all this data. You need to supply the dimension of it. Right now, we don't have automatic kind of dimension finding out. I'm not sure if anyone really has that yet. What in the document, what the embedding is, where it's found. So in the JSON, which kind of key corresponds to the embedding and which corresponds to the doc ID. So your primary key. And then overwrite will just, if a collection already exists here, we'll overwrite it. Usually in notebooks, we do that because if you run a step multiple times, you might start getting repeated data inside your vector database, and that's never fun. In this step, we're just taking our data and converting it into what LlamaIndex likes. So it has like this format of a text node, and it just holds the embedding, the text, and the ID. And we store also a relationship. So this kind of brings back, we have chunk IDs and doc IDs. So there are multiple chunk IDs per doc ID, and this has this relation. So when you break up like a single text source, you want to bring back, so if it's like a web page, if you have like 10 chunks of a web page, you want to get the source of those 10 chunks. And that's what we're doing with this relationship. And then we just create a list of those and we just add them to the vector store, and we got this successfully inserted. And the next step, we're kind of creating the engine. Again, this is with LlamaIndex, or this might be with LangChain actually. I think it's LangChain. So our service context, so our callback handler that's used for Arize Phoenix, it kind of gives data about the inferences so you can later go in and look at what was going on. So that's the callback there. We have our service context, which we have our predictor, which is the GPT 3.5 model. We have the embedding model, which is also OpenAI's embedding Ada model. And then we also have the callback. The index that we're using is the vector store that we created above. Yeah, this one right here. And that's going to be the index for our context. And then our query engine is just built on top of the index. I recommend looking into the documentation of LlamaIndex. You can kind of create more, or LangChain, you can create more complex, you can create simpler. But this is kind of a pretty basic one in terms of using vector databases. And here we just kind of have an example of testing it out. We ask 4 questions, and you can see down here what the questions are. How do I get an Arize API key? To get the Arize API key, yada, yada, yada. So this kind of shows that it is pulling all the data correctly. It's using the vector database to grab the relevant documents and summarizing it. And for all these, it mostly finds most of the prices, most of the answers. And yeah, so I'll kind of let you take over examining those responses and seeing how good they are.
Awesome, let's do it. Take over screen control here. All right. So what we're going to do now is to essentially take some of our data and store into data frames. This will allow us to load it into Phoenix super easy. I do want to take a moment to take a look at the data that we'll be ingesting. So the first is just that sample data, which is the data from our questions above. I'm not going to spend too much time on that, but I am going to come down here to where we'll download some data that we have stored for a bunch of queries that we've gotten for this chatbot. And we'll load that into what we're going to call our query data frame. And I'm making that distinction now because it will come into play later. And so let's take a look at some of the data that we'll be ingesting. So we have our prompt. So this is going to be our user query, but we also have our embedding for our prompt, as well as the response that we received from our LLM. We also created some tags that are really going to be helpful for us while we're doing our analysis, and we'll go through in a little bit how we actually calculate these. So the first 2 are going to be our similarity. We're returning 2 pieces of relevant text or similar text here. So we're going to have a similarity for 0 and as well as at the 1 position. We'll also ingest user feedback when we have it, as well as our document IDs, some scores. So that's going to be the actual similarity metric score for the prompt. And then we're also going to be using OpenAI to assess relevance here. And so let's get into how we calculated some of these. So for Oh, I guess before we do that, actually, let's go ahead and ingest our knowledge base. So we just took all of our docs and we loaded them into our vector database. Let's go ahead and pull that information and store it in a database, because what we'll do is when we're in Phoenix, we'll be able to compare our prompts or our user queries to what's in our knowledge base to identify some of those areas where we might have gaps or where our retrieval isn't performing well. So this is pretty straightforward. We're just going to use the vector store client and set that up, and then essentially iterate through all the data to pull out the document ID, text, and text vector to get our resulting data frame here. So you can see we have those columns that we just discussed, and we'll ingest this as our corpus data set into Phoenix. Cool. And here we're just doing some quick column mapping that's going to be required for us ingesting this into Phoenix. So we're going to have a embedding column for our database as well as our query. And so we're going to choose our text vector from our database. So that's going to be, going back up to this example, this column here for our knowledge base. And then for our query embedding column name, we're going to use the prompt embedding, which is the second column in that initial data set that we loaded. So now we have our data sets in our data frames. We've mapped out our columns for Phoenix. Now let's run some LLM assisted evaluations. So cosine and Euclidean distance are reasonable proxies for retrieval quality. So these are how similar documents are, but they're not always perfect for understanding how relevant the pieces of context were. So what we can do is do LLM assisted evaluation, where we can ask the LLM, is the retrieved context relevant to the user's question? And so here we give you the option to run it either with 3.5 or 4. It's up to you which you want to use, but if you have access to GPT-4, we highly recommend it. And so what we're doing is we're just getting our query text, then a list of our document IDs, and then we're also going to get a dictionary of our ID to the text so that we have that. And then we're just going to kind of iterate through those and determine whether or not the retrieved context is relevant. So we can see here an example of this happening. So we have our original query text from our user. We have the retrieved documents that were retrieved during our search and retrieval. And then we're doing this relevance score. So the LLM has determined if it's true, meaning it's relevant, or if it's false, it's going to be irrelevant pieces of context. And this is important because now what we can do is compute our ranking metrics. So for return 2 documents here, so we're going to calculate precision at K for 1 and 2. And it's pretty straightforward calculation here. It's similar to any time you would want to calculate these for other ranking metrics, except we're going to use those pre-calculated labels that we just created. And so we'll first do our first document relevances, get those all together, and then our second. And then we'll start our computation of those and add it to our data frame as these new columns. So we're also mapping out, sorry if I skipped that here. We're also mapping out true to irrelevant. I'm sorry, false to irrelevant and true to relevant. So if you remember up here, I said it was true or false. Now we're going to make these irrelevant, relevant labels that will be useful while we're reviewing these in Phoenix. So that's the end of kind of our data processing. So to review, we pulled data from our knowledge base into a data frame, and we downloaded some query data to put into a data frame. On that query data, we used LLM assisted evaluation to determine if our retrieved context was relevant or not. And we used those labels to then calculate precision and relevance at K. And now we're pretty much ready to start launching Phoenix. This is where things get interesting. Now we can really have the data ready so that we can begin root causing some of these issues. So here is going to be where we launch Phoenix. So we're going to define our knowledge base data set with the schema. So that's a pretty important step here is the schema. So we're going to map to a prediction ID. Here we're doing document ID for our database, as well as the prompt column name. So if you remember, we set these up earlier. We're going to invoke this embedding column names here and pointed at the vector column and the raw data. And then we can just initiate this Phoenix data set here. So we're passing in that database data frame with the schema that we just defined, as well as the name database. So this is going to be our knowledge base sent to Phoenix. The next thing we're going to do is go ahead and send in our query data set. And since this is already in open inference format, we can skip the schema step that we did in the last step. And so we just need to declare from open inference and then send in the query data frame. And that's it. We've sent all our data to Phoenix. Now we're ready to launch our session and we can really dive in. So once you run this, you can go ahead and click this link, or you can opt to view it in the notebook. It's up to you. I'm going to view it in the browser, and this is what it's going to look like when you open it. So you can see here the embeddings that I sent in, as well as those additional dimensions like similarity, precision, relevance, and user feedback, all ingested into the Phoenix UI. And so you can click here. I've already loaded it up for us in this tab here, and now we're able to view our embeddings in the lower dimensional visualization. So I'm going to go ahead and close this time series for now so we can get a nice view on our UMap here. And what's really cool is that we're automatically kind of clustering, or we are automatically clustering, but we're also automatically surfacing some interesting clusters that we're seeing. We could view these as poor performing clusters or clusters that maybe are lacking context. Depends on what metric you're using and what you're trying to evaluate. Right now, I'm using query distance. So this cluster here that's surfacing at the top here is saying that it's 100% queries. There's no knowledge base points in this cluster. And as we go down, you can see that there are more and more clusters with knowledge base data. And that's how they're also colorized right now as well. We have some options for you, so you can use correctness or a dimension to color by, and that's really helpful. I like to view it as adding a lens to your data. So when you add the color, you're able to look at your data through a new lens, and that can be really helpful. So I'm just going to check the chat before I move on. Looks like Philip's on the first one. Okay, so we got a question here about ingesting the knowledge base into Phoenix and asking whether we need to embed everything a second time, or do you need to use, or can you just use the embeddings present in the vector database? So we're actually using the embeddings from the vector database. Going back up to that code here, what we're doing is we're creating that client for the vector store and using that basically to pull all our data, and then we're iterating through that to pull out our embeddings, our document IDs, and our text into a data frame. So you don't have to embed it again. You can pull directly from your Zillis vector store here and get the information that you need to send to Phoenix. Let's see, check the chat, see if there's any others there. All right, cool.
I'm slowly typing answers out for all of these as well.
I saw you typing, so I figured I'd let you handle those things, Philip. So you got some of those questions. If I didn't answer them, it's because Philip's on it. Perfect. Okay. So I just kind of give you an overview of some of the different tools that are available to you with Phoenix. I want to kind of actually use them and see what insights we can find. So I already mentioned using query distance, but we have our user feedback in here. So what I'd really love to do is go ahead and do average user feedback. And so when I do that, what we can then do is sort by our lowest metric value. Now, giving you a little bit more context to what user feedback is, a -1 is going to be a bad response, and a +1 is going to be a thumbs up response. So these clusters that have all, an average of -1, these are clusters that are entirely made up of bad responses. And so I want to go back to the cluster that I was originally seeing be completely our corpus data. So you can see that these points here, they might have some additional corpus, but before we were looking at query density, it automatically surfaced cluster 23. Where did it go? Here it is. That was 100% queries. So that immediately caught my eye because that's telling me that there's no real similar there's no similar pieces of information in our knowledge base to these user queries. So that immediately got my attention. And I see here that perhaps it's not the lowest user feedback, but it still has a pretty low user feedback. So definitely something I want to drill into. So what I can do is then select that cluster. And what we're going to do is have that data available for you to start root causing. And let's take a look at what we see here. So we're seeing, does it ingest nulls? Does it support Snowflake? And taking a look at this, I'm seeing that our context is relevant here. So nothing standing out to me. overall, I think maybe there's some irrelevance. So deleting records, kind of just keeping tabs. And you kind of want to go through this process with your clusters, and you're able to really identify the clusters in the patterns that are causing, the issue. So with this one here, we noticed that there was no relevant, where did it go now? We noticed that there were no relevant pieces of documentation. I might want to check my knowledge base to see if maybe these pieces of information are missing, then perhaps I need to add them, or perhaps take a look at how we're chunking or our strategy to see if this data does exist, why it's not being properly retrieved. Let's go back up to our worst performing cluster here. So this is our worst performing cluster. You can see it has fully -1 feedback. And so let's start investigating this one a bit more. So I'm going to pull up this data and do what I just did for that other cluster, but for this cluster here. So what's interesting about this cluster that I'm seeing that I didn't see in that cluster of the other data sets is these all seem to be about one topic, and that's the cost of Arize. And you can see that there are some pieces of context in here, but as I'm looking at them, they're not really relevant to price. So we can see that problem of most similar does not always mean most relevant. So you can see here that these similarity scores are pretty high. They're pretty close to 1. That means that the embedding for the user query was similar to these documents, but you can see that with our OpenAI evaluation, they really weren't actually relevant. And as I see this through the other points, I'm going to see, similar patterns here of finding similar documents, but they're not relevant. And I happen to know that we don't have pricing documents in our knowledge base, and we can kind of see that here with this query only having, these 3 relevant pieces of context surfaced in this cluster. And so what this allows me to start doing is thinking through, how do I want to address this problem? Now, if you had pricing documents, it might make sense to add that to your knowledge base, and then your LM would then have the information it needs to appropriately answer these questions. But in our case, when we don't have when we don't have pricing documents in or available to put in our knowledge base, it might actually be a prompt engineering problem where we might need to explicitly tell the LLM if it doesn't have context, then to not respond, but also definitely want to troubleshoot our retrieval a little bit more, maybe experiment with our chunking strategies, what similarity metric we're using to improve the retrieval. But now we've really identified a gap in our knowledge base and a problem with our retrieval that we can then go and address. I'm going to pause here again, check out the questions. See, I think we are all answered thanks to Philip. There's some in here that are Milvus specific we'll get to at the end here, so no worries on that. So yeah, this is going to be essentially how you're empowered to root cause your issues. You can use our clusters that are automatically surfaced, leverage our metrics to identify, your bad responses, and then really drill into these clusters to identify patterns such as here where the pricing, these questions were all on pricing, and we know that there's no data in our knowledge base to do that, which will lead us to improving our retrieval and perhaps our prompt as well. So I think that's going to be the end of the Phoenix demonstration. Kind of call for questions if there's anything anybody is curious about here. So we got a question about handling permission content. So when you have a vector that may have metadata that we filter on to restrict content from a set of users, is there a mechanism to take these kinds of conditional circumstances into account? Absolutely. You can load in really any of this metadata in as tags. So going back to this page here, I've loaded in the similarity and user feedback as my tags, but if you have additional dimensions that you want to ingest, you can absolutely add those in as well. And then that allows you to kind of take that into account when you're doing your analysis, whether you're colorizing or in the root cause when you're investigating the data points, you would have that all available to you to see. No problem. Awesome. So yeah, just kind of iterating one more time, what Phoenix is going to allow you to do is have the workflows to really root cause the issues. I hear all the time that users are just tracking inputs and outputs, and that's not really allowing them to resolve issues with their LLM. It's just identifying that there's a problem. And so a tool like Phoenix is allow you to really drill into your data, visualize it, identify these patterns, and then actually take the action to resolve them. So kind of going back to our slides here. We do want to thank you all for joining. This is the link to the Phoenix repo. Feel free to leave us a star if you're inclined. Join our Slack community as well as the Milvus Slack community. And my email is there. Philip will get yours added to this before we send it out. But yeah, I think we can use this last few minutes here going over questions, unless Philip, there's anything you wanted to add.
I see some more questions. I can kind of go over some of the questions that were asked in terms of distance metrics, and I see there was a question about real-time data. I guess I'll start with the real-time data updating vectors and vector embeddings and vector DBs updating. We have an update kind of function now in 2.3 that was released. So we can update embeddings. If you are changing your model, that won't really work. Once you change your model, your latent space, kind of where you're embedding to, changes dramatically, and you can't really mix and match different models. So if you're gonna, like, let's say, update the model but keep the same dimension, you're gonna have to update all your data. If you're gonna update the dimension and like a new model that has a different dimension, you're gonna have to create a new collection. But otherwise, you can insert data all the time. You can set the consistency level of your searches. So read after writes works, so you can stream data in and constantly search it, and it will be searched. You can kind of lower those requirements to increase speeds, but there's a lot of switches that you can mess around with in terms of real-time data.
Yeah,
and
I think
then
that's a super important thing. We go back to talking about like why we should care, why we need search and retrieval, and I think that's one of the superpowers of it. Is you can always kind of have this real-time data added to your knowledge base, so your LLM always has the most recent information to use. So definitely want to highlight that there. But go ahead, sorry.
No worries. And then the other question is about kind of distance metrics. So kind of cosine versus L2. This one's kind of hard to answer. So someone mentioned how sentence transformers have very high similarity scores for two sentences with opposite words. So cosine versus L2, cosine looks at the angle, let's say, between the vectors. So a really popular example before, when you were just looking at word embeddings, is like king minus man equals queen. That's kind of where this angle comes into play. But once you start kind of expanding to an entire sentence, this logic tends to fall apart, and like both distance metrics end up being very, very similar. It's kind of like the idea of cursive dimensionality. You have too much data and these connections don't really work as much anymore. So when you're trying to decide between cosine and Euclidean distance, it's all about giving it a try and seeing kind of what your results are, if it's the direction you want to go in. Like sometimes we recommend for like text-based things, use cosine because we like that kind of angle thing with word embeddings, and most likely it might work a little better. For images, use Euclidean distance. But in reality, it all depends on your embeddings and kind of giving it a try and seeing how it works. Yeah, so those are kind of the main questions. And then difference between Zillows and Milvus. Zillows is just the SaaS offering for Milvus. And you already answered the Phoenix questions. So yeah, I think there's another Phoenix question in the chat for you.
Yes, it looks like we have a question on how you can basically take the information, the insights that we found in Phoenix, and communicate those to others. So they can absolutely, launch their own session of Phoenix and see with their own eyes. You can share as well. But I think what I see working really well is just kind of taking them through the story and identifying the insights simply, like by saying, like, looking at our embedding data, we've identified a gap in our knowledge base, and you can kind of abstract that information away from Phoenix so that it's really palatable for different customers. So I definitely recommend that. But Chris, I'd love to chat with you. We can definitely talk through this a little bit more. There's a lot of different ways you can share this information so that they can really understand. And I think when it comes to non-technical individuals, the best way to do that is really abstract the information out of Phoenix and then give it to them in that format. All right.
There's another question that popped up. If your knowledge bases are all over the enterprise and your question requires jumping through various DBs, would you suggest a graph DB approach? I'm not 100% sure. Like sure that could work, but you can also, I think, like you can always
I
just
would
make new tables for
consolidate.
different
Yeah.
enterprises. But yeah, I'm not too sure on that one.
Yeah, I haven't seen anybody, again, like you said, like I assume the GraphDB approach would work, but I haven't seen that particularly done yet. But I have seen, kind of creating this central knowledge base from the different knowledge bases across an enterprise. Very cool. We have a few minutes left. I'll do a final call for questions before we wrap up our presentation. Does implementing a RAG system on structured data make sense? I have some thoughts on this, but seeing as Philip, you are kind of the vector DB expert here, I'd love to hear your answer first.
Like you can always do it, I guess. You can kind of do like regular structured searches to get relevant documents. In reality, like creating an embedding over like a table does not really work well. Yeah, like creating embeddings over rows of data doesn't work well. So maybe you can embed things like descriptions, like let's say, I think you mentioned a restaurant search. Like you can embed the descriptions of the restaurant, the menu. You can kind of sort of grab all the sentences in the menu and see. But in terms of if you want to kind of use the semantic search based on structured data, it gets difficult at times. But I think RAG should still work because RAG you can just do the regular search on the kind of tabular data and then just have the LLM summarize and kind of create a nice output for it.
Yeah, I totally agree with that. My kind of caveat to that was going to be like it would depend on what the data is and what your use case is. So as you mentioned, like some of those tabular data just don't work that well, and then you'd essentially kind of also be reinventing the wheel because there's so many traditional ML approaches that work well with the structured data. So I think I would take those things into consideration. And they're asking about the retrieval can be text to SQL component, right? Not 100%. Are you aware of what they're talking about there?
For which one? The LLM
The
cache
follow-up
use
to
case? Oh,
the
can the
follow-up to the
retrieval
structured. Yeah.
retrieval can be text to SQL component, right? Yeah, I'm not 100% sure by the meaning of that.
Yeah, if the question is if you can generate SQL, that is possible, but I'm not sure other than
there
that
is
what they
some
mean.
work. I'm not 100% sure what the project is, but there is some work on using LLMs to generate like the SQL requests.
Hmm.
Like technically you could do that, yeah. I think everyone's saying the LangChain agent.
Yeah.
So yeah, you can do that. That should work. But yeah.
Awesome.
And then we got another question for the LLM question cache use case. Does Mills provide anything specific that we should consider? We're looking to start the question cache. So GPT cache is actually our project. So I don't know if that's something that is if that relates to the question, but there's a GPT cache. And yeah, I guess anything specific, we kind of built it around Milvus. I think there's a bunch of other vector databases in it, but we recommend Milvus for it. And yeah, GPT cache is just like a library / framework for caching LLM requests, so you don't have to constantly send requests that can get expensive. So if you have two semantically similar questions, it'll reach into the cache for the response and try to use that and maybe apply a small like a llama model across it to fine tune the response.
Awesome. That makes a lot of sense. So looks like you should definitely check out Milvus for your initial testing as well. Cool. Awesome. One last call for questions. If not, we'll wrap it up. We appreciate everybody for joining. A recording of this will be shared with you all, so be on the lookout for that. And if any questions come up after we sign off for today, feel free to reach us by email or in one of our Slack communities. Philip, anything else you'd like to end with?
No, that's pretty much it. I posted my email in the chat. I can post it again. So if anyone has any questions, you can send it there.
Perfect.
Awesome.
Thanks, everyone. And thanks, Phil, for joining me today to do this. I had a lot of fun and learned a lot. So looking forward to working with you next.
Awesome. Same.
Thanks, everyone.
Yeah. Have a good one.